Okay, hello. This time I'm going to explain the homework problem from section 5.5 of the Pearson calculus, which is about indefinite integral with substitution. Okay, so let's do the 28 problems. Number 1. The integral of 3 times 3x plus 12 to the power of 5 dx. And the direction is I have to use the u substitution. So let u is equal to 3x plus 12. Then du is 3 dx. Okay, so using a substitution, this becomes u raised to the power of 5 and 3 dx part, 3 dx part will become du. Use the power rule to integrate u to the power of 5. It's going to be u to the power of 6 and divided by 6. Okay, now bring back to x. It's going to be 1 over 6, 3x plus 12 to the power of 6 plus constant. After you do the integral, make sure to differentiate your result to check whether this really gives you this one after you differentiate it. Okay, number 2. It is 2x times x squared plus 1 to the power of negative 6 dx. And the direction is integrate by using the substitution u is equal to x squared plus 1. So again, let u is equal to x squared plus 1. Then du will be the derivative of this, which is 2x dx, which is actually here, 2x dx. After the substitution, this becomes u to the power of negative 6 times du. After integrating this, use the power rule, raise the power by 1, and divide it by negative 5. Don't forget to put back into the expression in terms of x. So u is x squared plus 1. So it's going to be negative 1/5 x squared plus 1 to the power of negative 5 plus c. Okay, again, make sure to check your answer by differentiating this. Okay, number 3. Integral of x over 5 minus x squared dx. Well, this is really same thing as x times 5 minus x squared to the power of negative 2. And in this sense, this is very similar to problem number 2. So the direction is, let's use the substitution. So let u is equal to 5 minus x squared. Then du will be negative 2x dx. So unfortunately, this one is not really equal to this part, but the difference is by just a constant multiple. So you can use this one to get the negative 1/2 du is equal to x times dx. So this part you can apply it to here. So after u substitution, it's going to be u to the power of negative 2 times negative 1/2 du. Put the constant in front of the integral. And you can use the power rule to integrate this. So raise the power by 1 and divide it by its reciprocal. So that's going to be 1/2 5 minus x squared to the power of -1 plus c, which is same thing as 1 over 2 times 5 minus x squared plus c as well. Okay. Okay, next one is complicated, a bit complicated. X cubed plus x squared to the power of 11 times 3x squared plus 2x dx. Well, if you do not have this part, maybe you have to expand this expression. However, luckily, we have this part, so the simple u substitution works. So let u is equal to x cubed plus x squared. Then du is 3x squared plus 2x dx, which is exactly the same as this part. So it is u to the 11 du. So the answer is going to be u to the 12th over 12 plus c. 1 over 12 x cubed plus x squared to the power of 12 plus c. Okay. So again, try to check your answer by differentiate this one. Okay. If you practice this one by checking many times, you probably will be able to integrate this one without writing down the u substitution steps. You probably can see it from this one to directly get to here. Okay, so next one, number 5. The integral of 12 y fourths 4y squared plus 8 squared and y cubed plus 2y dy. So unfortunately, this is exactly equal to this derivative of this part, but let's take u is equal to y to the 4th plus 4y squared plus 8. Then du will be y cubed plus 8y, and that dy. That is equal to 4 times y cubed plus 2y dy. Now you see this is equal to this, and only difference is a constant multiple, which can be done quickly, which can be handled very easily. So this becomes 12u squared times 1/4 du. So that's going to be 3 times u squared du. So the integral is going to be u cubed plus c. And put back to y. So y to the 4th, 4y squared plus 8 to the power of 3. Okay. And check your answer again. Okay. Well, this is just a review problem. It is just like a rewrite the fractional powers into radicals. And this is same thing as c to the power of 2 plus 1/3, which is same thing as c squared times c to the 1/3. Yeah, and that is equal to c squared times 1/3 is same thing as cubic root of c. So that's how you can rewrite it. Also, you can rewrite it as, if you just use as m over n is same thing as nth power of c to the power of m. Then c to the 7 over 3 is same thing as cube root of c to the power of 7. Yeah, and they are equal in this case. Yeah, one is like a simplest form inside the radical. Another one is just put 2 c's into 1 inside the radicals. Okay, so this is the same thing. This is a review problem about the sigma notation. So I'm gonna skip this. Again, this is just, you can use a formula. You can use a formula, or you can just add, because you just need to add 6 different numbers. So if you use the definition of the sigma, so when n is equal to 1, that's 3. When n is equal to 2, that's 6. When n is 3, it's 11. N is 4, it's 18. And n is 5, it's 27. N is 6, it's 38. And you can just take a sum like this way, which is 20, 38, 76, 103. Another way to do is you may use a formula if you remember it. So this is a sigma of the sum. Like the integral or derivatives, you can split the sigma into two parts and you can take a sum. This part means 2 plus 2 plus 2 plus 2 plus 2 plus 2. It is the same thing as 2 times 6. This part is the sum of the first n squareds. And if you remember the formula for the square one, that is n times n plus 1 times 2n plus 1. So if you use this formula with case n is equal to 6, n is equal to 6, then it's going to be 6 times 7 times 6 plus 7, which is 13. So that's going to become 12 plus 91, and that's going to be 103. Okay, go back to section 5.5. Problem number 10. Integral of square root of 9 minus 5s ds. This one is a case that you have a simple function like square root of x dx, and where the x is replaced by some linear functions. Okay. So when you have a antiderivative of a little f is actually equal to the capital F, then if x is replaced by some linear term ax plus b, then that is actually basically it's equal to capital F of the ax plus b. But because of the chain rule, you had to be careful that you had to divide it by a. Okay, so if this is the case, you can use basically the same integration formula to find the result by just be if it is a linear term inside. So think about this. So square root of x, integral over square root of x is equal to x to the 2/3 and well 3/2 times 2/3 plus c. That's the basics. So if I apply this one to this linear function here, it's going to be 3/2 and 2/3 plus c. And this 1 over a, going to take a row here. So you have to divide it by -5. So the answer is -2 over 15 of 9 minus 5s to the power of 3 over 2. Okay. This is just a result of the u substitution. And so if you don't feel comfortable with this, try the u substitution with u is equal to 9 minus 5s. Okay. However, when this one is a linear term, linear function ax plus b, we want to be able to solve this one without actually rewrite the expression in terms of u. We want to directly find the answer like this. Okay, number 11. 3 integral of 3 over square root of x, 1 plus 3 square root of x to the power of 6 dx. Now this one is complicated because inside the power of 6, well, power of -6, you don't have a linear term. So let's rewrite, let's say u is equal to inside the negative power of 6. So let's say u is equal to 1 plus 3 square root of x. Then du is 2 square root of x and 3 dx. And you see that this part is basically here, 3 over square root of x dx. The only difference is a constant multiple of 1/2. So that means 2 times du is 3 over square root of x dx. That's good. Perfect. So let's rewrite this in terms of u. So it's going to be u to the power of 6. And these orange parties become 2 du. So using a power rule, this is power of -6. So it's going to be power of -5 and divided by -5. So the result will be 2 over -5. And the u to the -5 is put in the bottom, raised to the power of 5. Okay, so that's the answer. Number 12. Now we have trig functions. And secant a8x plus 5 times tangent 8x plus 5 dx. Well, do you notice that this is a linear term and they are same? So basically this problem is same thing as secant of something times tangent of something, du. Almost. You have to be careful about 1/8 later, but this problem is basically almost identical with this one. Now, if you remember what function gives you this one after differentiated, and that is actually secant. So the answer should be like secant something plus c. Okay. So if you remember the formula about this, then you should be able to find the answer to this one immediately because it's going to be secant of 8x plus 5. Now, when you differentiate this, you're going to get secant tangent and the product multiplied by 8. So you had to divide it by 1/8. So that's 1/a appears. Okay, so this is just a linear term. So we can, the idea is something like this, but if you don't feel comfortable, try to use u is equal to 8x plus 5. In that case, you're gonna see 1/8 in front. Okay. Okay, this is just a review problem. Just a review. Number 13. This is a verified identity. So it's important. So we want to show that it's equal to this. So let's prove the identity. So here's the proof. Start from left-hand side of the equation. So left-hand side, you can see the top numerator part can be factored into the difference of squares. This is difference of squares. So it's going to be using a formula, a squared minus b squared equal to a minus b times a plus b. So you can factor it like this. Now you can reduce the fraction because it's in product form. So that's tangent x squared plus 1. And then this is actually equivalent to secant squared, which is the right-hand side. Okay. I hope you remember this part. The very important formula for the sine to cosine is cosine theta squared plus sine theta squared is equal to 1. That means when you divide both sides of the equation by the cosine square, they are still identical. And that is equal to 1 plus sine over cosine is tangent, and 1 over cosine is secant. So that's basically the Pythagorean theorem in different form that is applied here, okay? Now this is another review problem. So verify that the given trigonometric equation is the identity. So number 14, minus 2 over tangent alpha minus secant alpha plus minus 2 over tangent alpha plus secant alpha. Now, so here the problem is I had to fill in the blanks. So I had to follow this one. So on the left side of the given equation, so proof. So start with the left-hand side. The direction said rewrite the denominator in terms of sine and cosine. So tangent is sine and over cosine, and secant is 1 over cosine. So that is rewritten like this way. Now, type the terms of your expression in the same order as they appear in the original expression. Good. Okay, now this simplifies to this. What happened? Well, this is a mixed number, fraction inside a fraction. Yeah, it is a complicated expression. So let's multiply bottom and top by the same thing to eliminate the denominator fractions inside the fraction. So multiply top by cosine and bottom by cosine, and do the same thing here for the second fraction. So after you multiply the numerator by cosine and denominator by cosine, you will get this. Okay, multiply numerator by cosine, multiply denominator by cosine, then they don't change the value. Okay, now rewrite both terms of the expression using LCD. LCD means the least common divisor. Least common, yeah. So, so you're looking at this one and this one. You try to make the denominator same. In Japanese, this is tsubun. So let's do tsubun. So it's gonna be denominator will become this, and the first fraction you multiply top and bottom by sine alpha plus 1. Okay, that's first part. Plus the second fraction is multiplied top and bottom by sine alpha minus 1. So it's going to be minus 2 cosine alpha multiplied by sine alpha minus 1. That's this part. Now add the two fractions and simplify the numerator of the resulting fractions. So I'm gonna combine two fractions in this way and simplify the fraction. So the denominator doesn't change. So I'm gonna just write like this. And the numerator, you can expand it and simplify it. So I'm gonna abbreviate it like this. Something like this, where C is cosine alpha and S is sine alpha. So this is canceling each other, and you're gonna get -4 cosine alpha and sine alpha. Now bottom is when you expand it, you're gonna get sine square alpha minus 1. And that is equal to negative cosine square. Okay, so how do I get from here to here? Well, we use the cosine square plus sine square is equal to 1. The very important one here. Okay, so if you use this one, you can see that sine square is 1 minus cosine square, and you're gonna substitute this into here. Finally, you can reduce the fraction by divide top and bottom by minus cosine alpha. You're gonna get 4 sine over cosine, which is same thing as 4 tangent. And okay. Okay, number 15. Integrate 8 over t to the power of 9th of cosine 1 over t to the power of 8th minus 7 dt. Notice the derivative of the inside is here. This is power of negative 8, and the derivative of this one is on the outside multiplied. So it's how convenient. So let u is equal to 1 over t to the power of 8 minus 7. Then du is going to be, it's going to be negative 8 t to the power of 9 dt. Okay. So the only difference here is just a negative sign here. So negative du going to replace everything here. So this is going to be cosine of u times minus du. The integral of this is going to be negative sine u plus c, which is negative sine of 1 over t to the power of 8 minus 7 plus c. Okay. Again, differentiate this to make sure you get the same expression after you differentiate your answer. Okay, next one. 3 theta to the power of 4th sine 1 over theta cube and cosine 1 over theta cube d theta. Okay, looks complicated, but let's take it. This one is like you could think several ways, but the one idea is let's substitute u is equal to inside a sine function. That's one idea. Better idea in this question is let's put u is equal to sine 1 over theta cube. The reason is because if you substitute the entire sine function, then du gonna be include both the cosine part and theta to the power of 4th part. Do you see that this includes everything here? Okay, the only difference is just this negative sign. So if you plug in the u is equal to entire the sine function, then it's gonna be u times minus du. Okay, the cosine theta 4, 3, d theta, everything is together. So it's gonna become negative du. Okay, so that's gonna be negative 1/2 u squared plus c after integral, and bring back to the expression. So it's gonna be sine square of 1 over theta cube plus c. Okay, differentiate to check your answer. Now let's play a bit more. How about if we just try to do u is equal to 1 over theta cube only. Then du part going to include this one only. So after the integral, after substitution, it's gonna be sine of u, cosine of u, and minus du. So now you still have to integrate sine times cosine. So you might need another substitution. So let's say, for example, t is equal to cosine sine of u. Then dt is cosine of u du. So you have to do maybe multi steps, 2 steps. Substitute with u, then substitute with something else, and you're gonna get t minus dt. Then you're gonna get negative 1/2 t squared plus c. Then bring back t into u, which is this. Then bring back u into theta. So That's doable. That's doable, but you really need the multiple steps. Okay, this is one of the most computationally demanding one. Number 17. X over square root of x minus 11 dx. This one has a linear term inside the square root, but this question is not so easy. Idea is simple. Let's simplify inside the square root by substituting u is equal to x minus 11. Then du is 1 times dx. So it's simple to substitute. So it's going to be square root of u, and the dx going to be du. But what we should do is this part. When you substitute with a linear term, it is easy to solve for x. So, but if u is equal to x minus 11, then x can be written as in terms of u like this. So x is actually u plus 11. Okay, don't leave it as x. You want to change everything in terms of u. It's very important here. Okay, now what's the difference between the first expression and the expression in terms of u? Looks similar, but there's a huge difference. And the huge difference is that this fraction can be split into two simpler fractions. Okay? Because the denominator is a monomial, it's easy to split into two terms. So this is same thing as square root of u plus 11 over square root of u, where both of these can be easily integrated by the power rule. So it's going to be increase the power by 1 divided by 3/2. And this is power of negative 1/2. So after integrate, it's going to be u to the power of 1/2. Remember, this is same thing as u to the negative 1/2. So increase the power by 1, it's going to be 1/2. And you have to divide it by 1/2, which is basically multiplied by 2. So now bring back to the terms of x. So it's going to be x minus 11 to the power of 3/2. And bring back this one in terms of x as well, to the power of 1/2 or square root of that. Okay, so that's it. Well, let's play this one a little bit. Well, if you know why we do the substitution, then you probably do not need a substitution. The only reason for substituting this one is to make this one looks easy to split the fraction into two terms. So split the one fraction into two fractions. That's the whole point of this substitution. But the substitution doesn't change the nature of the expression. So if you know what's going on in these computations, you probably found out something like this. So this is u. Remember, you make this one as u plus 11. So you remember u plus 11. What is u? U is x minus 11. So what you are going to rewrite this expression is rewrite x as u plus 11. Okay. Then this is same thing as x minus 11 over square root of x minus 11 plus 11 over square root of x minus 11. Now this is going to be reduced to square root of x minus 11. And now you can integrate both of them without changing it into u. Well, this is because inside the linear term, it is 2/3. And it's going to be 22 x minus 11 to the power of 1/2. And that's faster if you can see this. Okay. Number 18. Integral of square root of x squared minus 2 over x to the fourth dx. Now, it's not clear what should I substitute this one with. So first of all, let's simplify the denominator. So denominator, you can put x to the power of fourth maybe out. So this expression is same thing as maybe put the x to the power of fourth out. So it's gonna be x to the fourth out on the denominator, and you wanna get x squared minus 2 dx. Now this is not so nice, because derivative of this one doesn't give you this. Derivative of this one doesn't give you this. So we cannot find a really good way to simplify this one by substitution. We cannot find a proper substitution. So let's try another way. So let's simplify this fraction by divide top and bottom by x squared, for example. Well, divide it into two fractions, let's say. So divide it into two fractions, it's going to be 1 over x to the power of 6 minus 2 over x to the power of 8. Is it simple? Maybe not, but let's put something out. Let's put something out. So if we put x to the power of 6 out, that's going to become x cubed. And let's try this one. So by factoring out by just x to the power of 6 out instead of 8. So when you put x to the cube out in the denominator, this is going to be 1, and this is going to be 2 over x squared. And that looks a better one than the previous one. Reason is, now you can see derivative of this one become this. The derivative of the power of negative 2 gives you power of negative 3. So now let inside the radical is u. Then du gonna be plus 4 over x cubed dx. Well, we don't like this 4 much, but it's just a constant multiple, so it's easy to substitute by just put 4 to the other side of the expression. Okay, so this is very useful. So after substituting this is gonna be square root of u, and the other part combined is become 1/4 du. Now you can integrate this one. You put 1/4 out, integrate this. It's going to be u to the 3/2 times 2/3. Simplify the expression. It's going to be 1 over 6. And put back u into x. So it's going to be 1 minus 2 over x squared to the power of 3/2 plus c. Okay. Okay, number 19. Okay, formal method is going to be put p plus 5 is u. Let u equal to p plus 5. Then du is going to be dp. So it's going to be, this going to be u to the power of 6, and dp is going to be du. But you want to keep remain with p here. So using this identity, p is equal to u minus 5. So we write the p in terms of u, so you want to get this. This is same thing as u to the power of 7 minus 5u to the power of 6. You see, this one is easily use a distribution or expand it. You don't want to expand this one, but you can expand this one quickly. Okay, now you can integrate it 1/8 u to the power of 8 minus 5/7 u to the power of 7 plus c. So maybe you can factor out u to the power of 7. So it's going to be 1/8u minus 5/7. Put 1/56 outside. So you multiply this one by 7. You multiply this one by 8. So this is a good factored form. And now you want to put back into x. No, p. So it's going to be p plus 5 to the power of 7. And it's going to be 7p minus 5 plus c. Where this is like p plus 5. So when you expand it, it's going to be 7p plus 35 minus 40. That's going to be 7p minus 5. And this is a more preferred solution than the one I posted to the left. Okay. In Japanese textbooks, the final answer is in factored form whenever possible. So this is a preferred answer than the one to the left. Okay, number 20. This is just a review problem. So I'm not going to explain fully. So number 20. Find the open interval on which the function is increasing and decreasing and identify the function's local maximum, absolute maximum, if any. So this is the application of the derivatives. So we want to differentiate this, but before differentiating this, let's divide the fraction because this expression has a power of 2 on the top, which is greater than power of 1 on the bottom. Use a synthetic division because that's easy. So the quotient is x plus 8 and the remainder is 1. So this expression is x plus 8 plus 1 over x minus 8. By rewriting the improper part fraction into mixed fraction, it's easy to differentiate. So differentiate each term, it's going to be 1 minus 1 over x minus 8 squared. Combine the fractions, it's going to be x minus 8 squared minus 1. Numerator is square minus square. So you can factor it. So x minus 8 plus 1 and x minus 8 minus 1. So that the derivative form in completely factored form. Now looking at the table, draw the diagram, x, f dash, and f. So the key values are critical point is 7 and 9. And also be careful that the x is equal to 8 is outside of domain. So 7, 8, and 9. Function is undefined at x is equal to 8. Derivative is 0 at 7 and 9. And this is, denominator is always positive. So just looking at the positive or negative from this quadratic function, which has a positive value on the two ends, negative value in between. So it's going to be up, down, down, up. So it's going to be, you have a local maximum here, local max here, and this is local minimum here. Okay. Do we have absolute maximum or absolute minimum? That's something you have to check the endpoint behavior. So, well, this is not the proper way of writing it, but basically you're gonna check how high this goes. Okay, because there's two possibilities. Like this local maximum could be the absolute maximum. But if you check these endpoints, if they have higher values, then this is not the absolute maximum, and there is no absolute maximum if this is the case. So you have to check the limit of the right endpoint of this function. And it is clear that when you plug in x is infinity here, it's going to be infinity plus 0, which is infinity. So the graph is going upward without bound. So there's no absolute maximum. So just the local maximum. And similarly, you can show that this has no local, no absolute minimum. This is a local minimum, but it's not the absolute minimum. Okay. Well, this is another review problem, so I'm not going to explain here, okay? This is a very simple problem. Integral of x to the power 5 over 6 minus x6 squared. Well, you see that the derivative of this one is here. How convenient, how convenient. So the obvious choice of u is u is equal to, so let u is equal to 6 minus x to 6. Then du is minus 6 x to the power 5 dx. We don't like this one much, but we are very happy with this part, and this is just a constant number, constant multiple, so you can just rewrite it in this way. So that's something very useful to hear. So it's going to be 1 over u square, 1 over u square times negative 1/6 du. So you can put negative 1/6 here. Integral of this one, using a power rule, it's going to be u to the power of -1 divided by -1 plus c. So it's going to be 1 over 6 times u to the power of negative 1. Okay. Oh. Okay, number 23. Integral of 4 over 4x plus 1 natural log of 4x plus 1 dx. You notice that they have same thing here. Remember that the derivative of ln x is 1 over x. So you see that if you put ln x as u, then you see that this part gonna be du. So let u is equal to the entire ln x, ln of 4x plus 1. Then du is 4x plus 1 on the bottom, and the derivative of this one is 4 dx. So you see, this is all here, okay? Okay, so after you substitute it, it's gonna be ln of u. No, ln of u. I include ln in u. So it's gonna be u here. This is u. And everything else combined together is du. So the integral of this one is gonna be ln of absolute value of u by the formula. And bring back that one into x. So it's gonna be ln of 4x plus 1. Okay. Looks ugly function, but differentiate to check that is equal to this one after you differentiate it. Okay, next one. Next one is hard one. 21 over 4 plus 25 r squared dr. one formula is integral of this is equal to the arctangent of x. So this is the formula that we are interested to use. Unfortunately, we don't have a similar structure, number over number plus x squared, but slight differences here. So in this case, here is the idea to use. So when you have a squared plus b squared here, you want to set this is basically 5r squared. 5r is equal to 2u. Or 5r equal to 2u. 2 is coming from here. Or you can just say when you have a squared plus b squared, then consider about the substitution of b over a squared instead. Okay, so it's going to be 5r over 2 is equal to u. Then du is going to be 5 over 2. Now let's see what's going to happen. So these numbers doesn't change, but because 5r over 2 is, because 5r is equal to 2u, 25r squared is 4u squared. So this is going to be 4u squared and times, sorry, this is dr here. So, and this is going to be times 5 over 2. Sorry, it's missing here. I had to change it here. So this is dr is equal to 2 over 5 du. So it's going to be 2 over 5 du here. Now you can put 5 and 4 and 2 out. So, well, and 21 out. So numerator going to be 42. And denominator, you put 20 out. Then the bottom numerator become 1 du. And the denominator is after factor out 4, you're going to get 1 plus u squared. So now you can use this formula, arctangent. So it's going to be arctangent of u plus c by the formula. Bring back u into x, so it's going to be 21 over 10 arctangent of 5r over 2 plus c. Okay. So like a structure is like something square plus something square 1. If you see something like this, that's the arctangent problem. Okay, now next one is another inverse trig function involved. E to the inverse sine of x over square root of 1 minus x squared dx. Looks very complicated. Let's review some formula. A derivative of inverse sine function is 1 over square root of 1 minus x squared. Do you see? So the derivative of this part is here. How convenient here again. So let u is equal to the inside of the exponential function. Then du is 1 over square root of 1 minus x squared dx. So after substitution, it's going to be e to the power of u times du. This is everything together is du. So now integral of this is just e to the u plus c and bring back to x. So if you know it, it's simple. So make sure to have a formula sheet for derivatives somewhere. It's easy to access. Okay, 3 more questions. Number 26. Now this is the initial value problem where s dash is equal to 28t 70 squared minus 5 cubed and s of 1 is equal to 6. So initial condition is given. So let's find s. So s of t is, you can integrate its derivative in terms of t. So you just need to integrate the derivative. Now, this one is a very simple one. So this is a quadratic inside the cube function, and whose derivative is basically here. So after you do some u substitution, you probably get 70 squared minus 5 to the power 4th, and it's going to be 1/2 here plus c. Okay, so after you do integration, you want to get this. Now, because s of 1 is equal to 6, you plug in 1 here. You plug in 1 here, so it's going to be 7 minus 5 to the power 4th plus c. That should equal to 6. Now this is going to be 8 plus c is equal to 6. So c is equal to minus 2. So the conclusion is s of t is 1/2 70 squared minus 5 to the power 4 plus c. Okay. Okay, again, this is another initial value problem. So now you have a second derivative. Second order derivative of s is negative 16 cosine 40 plus 5 pi. And the two initial conditions, s dash of 0 is 500 and s of 0 is equal to 0. Now let's find s dash. S dash is the integral of s dash dash with respect to t. And when you integrate this one, this is a linear term, so integral of cosine will be sine. It's going to be so negative 16 sine 40 plus pi. And when you divide this one, remember, you should forget it. Don't forget about divided by 4 and plus c. So that's s dash. Since s dash of 0 is 500, so you plug in 0 into here, you want to get sine of pi times negative 4 plus c. That is equal to 500. But because sine pi is 0, that means c is 500. So that means s dash of t is minus 4 sine of 40 plus pi plus 500. Now let's integrate this one once again to find s of t. So you want to integrate this one. And you can integrate this one. You want to get the minus, will actually become plus cosine 40 plus 5 plus integral of 500, which is 500t, plus some constant again. Now because s of 0 is 0, since s of 0 is 0, s of 0 is, you plug in 0 here, it's going to be cosine of pi. 500 times 0 is 0, and plus c, and that is equal to 0. Well, cosine pi is negative 1, so c should be equal to 1. Well, I should say c2. Let's say c2 to distinguish it from this one. So the final answer is s of t is cosine 40 plus pi plus 500t plus c2, which is plus 1. Okay, last question. Number 28. The velocity of a particle moving back and forth on a line is, well, velocity is basically derivative of the position function, and that is given by 8 sine of 2t, unit is meter per second. And we know that s is 0 when t is 0. So we know that s is in function of t, and we know that s of 0 is equal to 0. So that's the initial condition. Okay, now question is, find the value of s when t is 2 pi over 2. So we want to find s of pi over 2. So with these two informations, you can find s of t first by integrating s dash. So that means you want to integrate 8 sine of 2t dt. So after integrated, you want to get -4 cosine of 2t plus c. Now, using this initial condition, you can see that she's from s of 0 equal to 0, you can find that c is equal to 4. So s of t is equal to -4 cosine 2t plus 4. Now it's easy to just find s of pi over 2. Just plug in pi over 2. So it's going to be cosine of pi here. And cosine of pi is -1. So it's going to be 4 plus 4. And that's equal to 8. Okay. So the answer is 8 meters. So that finished the explanation for section 5.5. In section 5.6, we still are going to do the integration by substitution, but we want to do it with the definite integrals.